Welcome to the fourth video of this presentation called What Goes Inside an iPhone. The study of the iPhone was divided into 5 blocks called Energy and Mainboard, Access, Radios and Antennas, Movement and Location, and finally Cameras. But there is an important introduction which establishes a common ground. So we are now in the subject of Access, which deals with the main ways of interfacing with a smartphone. So let me show all the videos. Here they are. If you haven't watched 1, 2, or 3, I suggest that you do that before you proceed. Today's video is about the display, which includes also the touch screen. So here we go. Display is another interesting subject. In the case of smartphones, it consists of 2 parts, the display proper and the touch screen. Even though they are built together, they are independent devices, the display being an output device, while the touch screen is an input device. I'll start with the display, but instead of going straight to the iPhone, I'll show the evolution of TV monitors because it encompasses the entire history of electronic displays. Understanding the iPhone displays after that will be straightforward. Okay, the evolution of TV monitors. It started with the CRT, cathode ray tube TV, then the LCD, liquid crystal display TV, which was the first flat panel TV. Next was the LED, light emitting diode TV, then the OLED, organic LED TV, and finally the QLED, quantum dot LED TV. 2 technologies under research are the QLED TV, but the electroemissive version. This is the photoemissive, and the micro LED TV. All of this will be seen in the slides that follow. I'd like to start by showing the big picture because it will help in the continuation. As mentioned, the first flat panel TV was the so-called LCD TV. Because liquid crystal displays do not generate light, a backlight is then needed, which was produced then by fluorescent lamps, later replaced with LEDs. The 2 main components here then are the LCD and the backlight. These components, plus the main components of all displays that followed, are described next. The first component is the LCD. You can think of it for now as a sheet of glass whose transparency is controlled by a voltage. In this example, with 0 volt, it is completely transparent, so the light that arrives passes through. With a middle voltage, the light is attenuated, and finally, when the voltage is maximum, it becomes completely opaque. It can also be constructed to do the opposite of this. The second component is the LED. It's a little device that emits light when an electric current flows through it. The next one is the organic LED. It does the same as the regular LED, but it is much smaller and also much more difficult to build. The fact that it is small is good because you can then implement pixels directly with this device, which is not possible yet, at least with regular LEDs. Next is the color filter, which is a material that allows only one color to pass through, in this case, red. In practice, it is a thin film applied on a substrate like glass, for example. In this other case, 3 monochromatic colors are received, 2 are blocked, and red passes through. Finally, there is a special notation. These blue and yellow arrows together do not mean that it is monochromatic blue and monochromatic yellow, but rather it is a large spectrum with a main peak at blue and a secondary peak at yellow. So with enough energy to get any color at the output. The final component is the quantum dot color converter. It is a material that absorbs blue or violet light and re-emits it in another color. It has 2 major advantages over color filters. First, it does not have the energy loss due to blocking, as illustrated here, for example, for green and blue. And second, its output is closer to ideal monochromatic light than it is at the output of color filters. Okay, knowing the components, we can use them now to show how current TV displays are constructed. First, the LED TV. The display is here. It's a liquid crystal display. The LEDs play only the role of backlight. So you have the backlight, the display, and then the color filter. The OLED TV. I mentioned that OLEDs are small enough so they can play the role of pixels directly. And that's the reason why there is no need now for backlight. So you get rid of the backlight and of the LCD, and you put OLED in their place. And then you have the color filter. Also, you can have the OLEDs emit directly the colors that you want. But for large devices like large TVs, there are technical problems like alignment, things like that. So you will see the color filter in large displays. Finally, the QLED TV. Notice that this figure here is the same as the LED TV, just with an additional layer. It's the quantum dot color converter. But this is all blue, so there is no loss. As I mentioned, there is no blocking, which is converted to the intended light. One thing that looks redundant here is that why have this one plus this one? So it might be that in the future, this is just moved to this position and you get rid of the color filter. We saw the big picture. So we turn now to internal details of the main types of TVs currently available, starting with the LED TV. Two main construction approaches are shown here. Remember that the LEDs are just for the backlight around the edge here, in a full array in the other case here. The edge backlight style was introduced by Sony in 2008. To get white light, the LEDs are indeed a three-element LEDs, red, green, and blue. So the result is white. The display is very thin, just 1 centimeter, and it's lighter with less power consumption and lower cost than the full array option. The full array construction was also introduced by Sony, this time in 2004, again using tri-LEDs to get white light. And its advantage is obvious, a better picture than that one, especially because in some monitors, the video signal can modulate the intensity of the LEDs, which helps improve the image quality. As we saw before, the display of an LED TV consists of three main elements: the LED backlight, the display proper, which is a liquid crystal display, and the color filter. All three are described in detail next. So I'll start by describing the light emitting diode. As mentioned before, it is a device that emits light when an electric current flows through it. You probably have seen this kind of device around. This is the newest addition to the family. It is used for lighting. It is a blue LED with this yellowish coating over it. I'll explain in a second how it works. The construction can be done with a single semiconductor. In this example, gallium arsenide. This semiconductor is doped to create a region with free positive charges and another region with negative free charges. This can be done for P by replacing gallium with zinc, for example, or arsenic with silicon, and for N by replacing gallium with silicon or arsenic with sulfur. By the way, gallium arsenide is one of the first LED materials, and it radiates in the infrared spectrum, so it cannot be seen. A typical application is then in the construction of remote controls by replacing some atoms of arsenic with phosphorus, for example. It radiates a red light. By changing the compositions and by playing with other materials, you get other colors, eventually getting down here, where indium gallium nitride and gallium nitride are shown, which are very important because they allowed the construction of highly efficient blue LEDs, which made light impossible using LEDs. The principle of operation is very simple. You apply a voltage which causes a current to flow through the device. As far as the current keeps going, light keeps coming out. This occurs because the injected carriers recombine, some of them recombine. When that happens, light is emitted. In this example, this electrode is transparent while this one is reflective, so light tends to come out through this surface. This dimension is assumed to be much smaller than this dimension here. A very important point is how do we get the red, green, and blue or white light from LEDs? There are two ways. First, by using a 3-element LED. This is illustrated here, so it is just 3 LEDs encapsulated together. The second is by using a blue LED with a phosphor coating. This is illustrated here in the second plot. Part of the energy from the blue light is absorbed by the coating and is re-emitted with this spectrum here, which is centered about the yellow. So the final spectrum is this one, which has enough energy in red, green, and blue to be extracted using the color filters. Just as a side note, red, green, and blue can also be obtained using quantum dots, which will be described later. To close this topic on LEDs, I would like to acknowledge some people who made a huge difference. So here are the Nobel Prize winners in physics in 2014 for the invention of the efficient blue LED, which led to LED-based lighting, which, by the way, was a development with major financial and environmental consequences. We saw the part relative to LEDs, so we move now to the liquid crystal display, which is responsible for producing the images. But what is a liquid crystal? In few words, it is a material with some properties of liquids and some of crystals, which are solids, like the following. In crystals, the molecules have fixed position and fixed orientation. In liquids, the molecules can flow, so they have a random position and random orientation. In liquid crystals, the molecules can flow, but they may have fixed orientation. Examples of liquid crystal materials are proteins, cell membranes, soaps, and many more. But for displays, the typical material is these two benzene rings with attachments. There are two main types of LCDs called TN LCD from the 1970s, and the current one, which is called IPS LCD, first delivered by Hitachi in 1996. Obviously, many improvements occurred along the years. Okay, starting with the TN LCD. The name TN is due to the fact that it is based on the twisted nematic field effect, which has to do with this twisted structure here. Before I describe the construction, a few words about polarizers. Light has two components, an electric field and a magnetic field, which are always perpendicular to each other. A polarizer is a material that allows only light whose electric field is parallel to the polarization of the material to pass through. In this example, there is a vertical polarizer here, so only the component and many polarizations arriving, only the component whose electric field is vertical will go through. In this example, the second polarizer is horizontal, so the back of it will be dark. Okay, now we can talk about the construction, but let me go straight to the figure. By the way, these colors are just illustrative because the material is indeed transparent. Uh, this, this layer between the two red plates is the liquid crystal. It is very thin, but it was enlarged here so we can see what happens inside. Let me go through the composition. A polarizer, glass plate, the first electrode made of ITO, indium tin oxide, which is a conductive material and is transparent, and then a rubbed polymer coated on top of the electrode. Then the liquid crystal, of course, and then the opposite, a rubbed polymer, the second electrode, the second glass plate, and the final polarizer. Just as a side note, the color filter, which is the element that we're going to see next, is usually coated on this glass plate here. Notice that the polarizers are perpendicular to each other, and the grooves on the polymers are parallel to the corresponding polarizers. The importance of these grooves is the following. The liquid crystal molecules tended to align with grooves. So the first molecule here aligns with the grooves down here, and the last up here aligns with the grooves up here. So this twisted structure results in between. So light that passes the first polarizer travels through this twisted structure, gets up here aligned with the second polarizer, so it goes through. Notice that this is the situation with the switch open. If we close the switch, a voltage is applied between the two electrodes, creating a vertical electric field. Because the liquid crystal molecules are aligned to the electric field, the light that passes the first polarizer no longer rotates, so it's blocked by the second polarizer. In summary, with zero voltage, the pixel looks white because the backlight comes out, while with maximum voltage, it looks black. Question, can we have the opposite? That is, with zero voltage to have the pixel look black, and with maximum voltage to have it look white? I leave that to you. Now the IPS display. It's called IPS, which means in-plane switching, because the electric field is now parallel to the plates, or in the same plane. The construction is illustrated in the figures. The first figure shows the two electrodes. So instead of having one down here and one up there as before, they are now on the same glass plate. When there is no voltage applied, the situation is exactly the same as before. There is a vertical polarizer here and an horizontal polarizer there. So light that passes here, only the vertical light passes, twists, becomes horizontal and goes through. The second one, in the second case, with voltage applied, there is an electric field between the two electrodes, so the molecules align horizontally to the planes now. So the light that enters here gets only vertically polarized light goes through, does not twist, so it's blocked by the horizontal polarizer. Conclusion, with zero voltage, the pixel is white, and with maximum voltage, it is black. Questions. First, how can we have the opposite? Meaning, with zero voltage, the pixel to be black, and with maximum voltage to have it white. Second question, very important. Do we need the twisted magnetic field effect for IPS? I leave them to you. Advantages of IPS over TN: better color, better contrast, wider viewing angle with no color distortion. This is very important. And no tailing when touched. It's important for touch screens. Disadvantages, slightly slower, but still fast enough even for games, and a bit more expensive. Having seen how LCDs are constructed, we turn now to some internal details, which are pixels, active matrix addressing, and TFTs. As you know, to create a pixel, the display is divided into small regions called subpixels, where each subpixel encodes the intensity of one of the fundamental colors, and by putting three subpixels of different colors together, we get a pixel. The interesting part is how these pixels are constructed physically and how they are addressed. Remember that the LCD requires two electrodes, so we can use one common to all the subpixels, but the other one must be broken into one per subpixel. This is illustrated here. So this is a subpixel, and this is the electrode. So there is one electrode, a different electrode for each subpixel. The other one not shown here is common to all of them. And the TFT thin film transistor is used to access each subpixel individually. So here's a transistor. You place the voltage that you want to store here on this line, then to activate this line, and this voltage is written or is stored on this electrode. The TFT is just a MOSFET or MOS transistor fabricated on amorphous silicon, which is it's a low cost, very light material. The voltage is written to the electrode sequentially and continuously, and it is held by the parasitic capacitance of the electrode itself, or by also an auxiliary capacitor built together with the transistor. The final element of our display is the color filter, shown here after the LCD. In practice, it is usually constructed on the final glass plate of the LCD. This is just to give an idea about pixel sizes in smartphones. For iPhone 11 and iPhone 11 Pro, the sizes are approximately 80 by 80 and 60 by 60 micrometers. The fabrication of the color filter is illustrated here using a process from BASF. It starts with a glass substrate on which a black photoresist is deposited. Then, using masks, ultraviolet light, and chemicals, the material is removed from certain areas, resulting in this pattern here. Next, the entire filter is covered with red filter, and using again UV masks and chemicals, red is removed from certain regions. By repeating it for green and blue, the entire filter results. I'd like to present some final comments on LED TV. LEDs are just for the backlight. The actual display is still LCD, so LED TV is not an accurate designation. LED backlit LCD TV would be more precise. However, LEDs brought important improvements like the following: better picture. For example, in full array local dimming monitors, the LEDs are controlled dynamically by the video signal, so the backlight intensity can be adjusted by regions, which has an enormous impact on picture quality. Much thinner and much lighter monitor, less heat, less power consumption, faster response, and much more. So maybe LED TV is not a bad name after all. I leave this for you to judge. The main part in an LED TV display is the LCD, so it is important to acknowledge a person who has made a huge contribution. Here's the Nobel Prize winner in physics in 1991 for studies on liquid crystals and other materials. Okay, the next is OLED TV. Just for comparison, here is the LED TV display just seen. The LEDs play just the role of backlight. In the case of the OLED TV display, the OLEDs being very small can play the role of pixels directly, so there is no need for backlight or for some other kind of display. Therefore, OLED TV is a precise designation. But what is an OLED? It is a device that emits light when an electric current flows through it, which is the same thing I said for regular LEDs. But instead of a semiconductor, it uses conductive polymers, or sheets of plastic, and that's quite impressive. Typical construction is shown here. It's built on a substrate. I'm just showing it upside down because I want the light to go up and not down. So here's the substrate, which is glass. There are two electrodes. This one is transparent, so it has to be conductive and transparent. So the natural candidate is ITO, which is indium tin oxide. We saw this before. And this is just a reflective material. It can be aluminum, for example. And in between, there are the layers of organic materials, which are the conductive polymers. Let's see the operation of this device. A voltage is applied between anode and cathode, which produces a current. As far as the current keeps going, light keeps coming out. So this happens because the carriers recombine. When that happens, light is emitted. If it goes in this direction, it goes out directly. If it goes down, it bounces in this reflective material and goes out through that surface. It is assumed that this dimension is much smaller than this dimension here. So OLEDs can be very small, so they can be used as pixels directly. So this is the very first self-emissive display. LCD and backlight not needed. So OLED, as I said already, is an accurate designation. Advantages compared to previous displays. The only self-emissive display available so far, better picture, no backlight, that's a true black, faster, larger viewing angle, thinner and lighter, lower power consumption, great for mobile devices. This iPhone 11, for example, 11 Pro. Best contrast of all current displays. Disadvantages for now, shorter lifetime and higher cost. Major developers for large displays, for TVs, in other words, LG. For small displays, including iPhone, Samsung display. To close the topic on OLEDs, it's important once again to acknowledge people who made the difference. So here are the Nobel Prize winners in chemistry in 2000 for the studies on conductive polymers, which led to the OLED. QLED TV is next. Just for comparison, here is the LED TV display once again, and here is the QLED TV display. Notice that the only difference is this additional layer constructed with quantum dot color converters. A minor detail is that blue light suffices because that's the color absorbed by the quantum dots. So in summary, this is equivalent to this display, but with a better backlight. If this layer can be moved to this position, then the color filter can be eliminated. But what are quantum dots? First, there are two types called photoemissive and electroemissive. In the case of a photoemissive quantum dots, there is no generation of light. Instead, it absorbs blue or violet light and re-emits it in another color. The color depends on the size and material of the dots. Notice that the size is very small. It goes here from 1 nanometer to 3 nanometers. This image is from NanoSys, which is a company that manufactures this kind of material. The major feature here is that the output here is a highly monochromatic light. In the case of electroemissive quantum dots, light is emitted in response to an electric current, so exactly as in LEDs and OLEDs. So this one can be used as pixels. So this is the big target in terms of QDs, and is an area under research. today's QLED TVs, only with photoemissive quantum dots. Main feature, better monochromatic red, green, and blue light, but black backlight and LCD still needed, so QLED TV is not an accurate designation. Major developer, Samsung Display. We close the description of displays with some comments on possible future implementations. The first is with micro LEDs, which have to be small enough to play the role of pixels. In this example, outputting blue and yellow broad spectrum, then a color filter is needed. In the second case here, if the output is monochromatic enough or depending on the application, done directly. The second case is with a combination of micro LEDs and quantum dots. In this case, the micro LEDs would emit blue light, which would be converted into very high quality red, green, and blue. The final case is with electroemissive quantum dots. So the light would be generated automatically with very high quality. Finally, we are ready to talk about the iPhone displays. So here are the last 3 years, and here is what you get. In the basic models, you get an LCD display of IPS type. That's a good display. But in the top models, you get an OLED display, which is about the best you can get. We turn now to part 2, which deals with the touch screen. It is indeed much shorter than part 1. The touch screen is built over but is integrated to the display. Main construction approach, using a resistive grid, using an infrared grid, or using a capacitive grid. This is the option used in smartphones, but it has 4 sub-options here: surface or projected, self or mutual. In the case of our smartphones, it is capacitive, projected, and mutual. Main materials, which must be transparent, obviously. For the substrate, glass or polyester, and for the capacitor plate electrodes, as usual, ITO, indium tin oxide, which is coated over the substrate. Example of self-capacitive touchscreen. We saw this already in the case of the fingerprint identifier. Here it is. So we have here the bottom plate of a capacitor. The upper plate here is formed by the finger. So the sensing circuit notes that this becomes a large capacitance. So there is no interaction between the plates, between the capacitors, sorry. So that's the reason why it's called self-capacitive. The projected capacitive with mutual capacitance approach. This is a general illustration of the operating principle. Here's the substrate, which is glass in this case. Here are 2 electrodes made of ITO, as mentioned before. In this case, the touchscreen controller sends the excitation through this electrode and reads it out through this other electrode here. Notice that they are not facing each other, the 2 plates. They are side by side, so the capacitance is their mutual capacitance is very small, typically in the picofarad range. The electric field can be modeled like this. There's an approximation. If there is a ground plane here, then it would go down also, but it's just an approximation. The amount of charge induced here depends on the capacitance, which is shown here, and the voltage applied, in this case by the touchscreen controller. If a finger approaches the display, it is equivalent to approaching another capacitor plate, not a great ground in the body, but good enough to alter the amount of charge here, split the charge. So this reduction of charge here with the same voltage applied means a reduction of capacitance, which is detected by the touchscreen controller. An example of implementation using diamond shapes is shown next. In yellow and blue are the plates of our capacitors, and in pink is the insulator. These colors are obviously just illustrative because these materials are transparent. Above the yellow plate goes the glass plate. Fingers do not touch the conductive parts. Looking more closely, we see that the yellow columns do not overlap the blue rows. They are very close, but they do not overlap. So they are quite similar to the side-by-side plates that we saw before in the previous slide. The working principle is as follows. One column is excited and all rows are read out. Then the next column is excited, all rows are read out again, scanning the entire screen several times during a touch, so allowing multiple simultaneous touches to be detected. In modern touch screens, this number can be as high as 20. Obviously, a fingertip is much larger than a single diamond. So when a touch occurs, it affects many rows and many columns. So a large number of calculations must be performed by the touchscreen controller in order to determine the most likely center of the touch, which is especially true when multiple simultaneous touches occur. And with that, we conclude video number 4. I thank you for watching, and I invite you to join me again for video number 5.